All right, good morning, everybody. This is the second section of chapter 14, and also the last one you will cover in honors chemistry for this school year. I'm proud of every single one of you for making it this far. All right, so let's get started. A couple of things that we're going to go over in this section involve definitions of acids and bases. On your quiz on Friday, you will be expected to label different characteristics about different species. So for instance, I'll give you something like HCl and ask you to label it. Is it a Bronsted-Lowry acid, a Bronsted-Lowry base? It may fall under multiple definitions, so make sure you have those definitions in front of you. For instance, it may also be an Arrhenius acid or an Arrhenius base or a Lewis acid or a Lewis base. So pay attention to the different definitions of the acids and bases in the first and second sections of this chapter. That is a very big topic, and I can guarantee I will ask you multiple times to identify things, and you will have to identify them correctly. They're correct only if you get all of the possible labels correct. Okay, and we'll talk about towards the middle-ish how we can also label them as mono or diprotic acids or mono or dihydroxy bases, I guess will be the term. And what that just means is how many protons will it have or how many hydroxide groups will it have when it dissociates. So let's get started. Bronsted-Lowry acid is going to be something that is a proton donor. And if you do not know what a proton is, at this point, a proton is defined as an H. Okay, just an H straight up that gets donated from one thing to another. So if we look down here, our HCl is going to be a Bronsted-Lowry acid because it takes a proton, so the H that it has, and it gives it to a base, NH3. And we know this happens because on the product side of this equation, we have chlorine minus the hydrogen, and we have NH4 with a positive charge. So protons are not only just H's, they're also positively charged. They have a 1+ charge. Water can also act as a Bronsted-Lowry acid, and water is special because water can act as either the acid or the base. But in this case, water acts as the acid because NH3 is the base. So water will act as either the acid or the base depending on what it's added to. If water is added to a base, then it acts like an acid. If water is added to an acid, then it acts like a base. And we'll see an example here in a second. But for now, H2O is going to give up one of its hydrogens, one of its protons, to NH3 to form NH4+, and it leaves behind an OH group. All right, a Bronsted-Lowry base is going to be a proton acceptor. So by definition, if an acid is a proton donor, a base in the Bronsted-Lowry definition has to be a proton acceptor. And these are the two most common definitions that we live by as far as acids and bases are concerned in acid-base chemistry. So make sure we've got these two down at the very least. Ammonia, in this case, is defined as the Bronsted-Lowry base because it has a lone pair when you draw the Lewis structure. So we can determine if something is a base or an acid by drawing Lewis structures. And I'm going to recommend that you go back and watch a video on Khan Academy on how to identify that lone pair by drawing those Lewis structures again, which we've done before. The OH minus being produced in solution by bases like NaOH is going to be the Bronsted-Lowry base itself. So anytime you see an OH, you can pretty much determine that that is going to be a Bronsted-Lowry base also. So just kind of keep that in mind moving forward. Anytime you see an OH minus in a species of any kind, you can define that as a Bronsted-Lowry base. Okay. Additionally, you define any Bronsted-Lowry, any species as a base in this particular definition if it can accept a proton and become positively charged. All right, in an acid-base reaction of Bronsted-Lowry, what we're going to see is we can define something as an acid and a base. By defining that, on the right side of the equation, we can also see where the proton goes and where the proton leaves, right? So we saw that the chlorine lost its proton, and we saw the NH3 gained that proton. Monoprotic and diprotic acids are our next topics. Monoprotic just means it only has one proton to donate. So something like HCl only has that one hydrogen that it can donate. And once it does that, it's no longer an acid in any way. So anything that is monoprotic is an acid that can only donate that one hydrogen atom. A diprotic acid, on the other hand, is going to be something that can, in theory, donate more than one hydrogen. So for instance, H2SO4 has 2 protons in front. Once it donates the first proton, it still has 1 left over, the HSO4, that it can donate. Once it donates that though, then it only has the SO4 minus ion, or the SO4 minus ion, and there's no more protons for it to donate. So we can identify a polyprotic acid, which is something that is not mono, by looking at how many protons there are in the front of that particular reaction. Down here, what that means is that it can undergo more than one acid-base reaction. So in the first step here, we see H2SO4, which is of course our acid. By definition, it's the proton donor. And because it's the acid, the water here also acts as a base. And that water molecule is going to accept a proton from H2SO4 and form another H3O plus, which is just another proton, and then HSO4 minus. And that HSO4 minus is the thing that we take in the second step, and we're going to remove that proton again adding to water because water can act as an acid or a base. That water gains that proton and it leaves behind the species that has no more protons. In that case, this SO4 minus can no longer act as an acid under the Bronsted-Lowry definition. Now, we can give further definitions to that. We can say monoprotic or polyprotic. We can also say diprotic or triprotic, di meaning 2 protons and tri meaning 3 protons. Don't get hung up on this. I would likely ask you mono or poly. If you see a question that is asking you about di or triprotic, I might just be asking you, is this a diprotic acid or a triprotic acid? Nothing along the lines of, is this mono, di, or tri? I just don't think that's very helpful. So I would be looking for, is this a monoprotic acid or a polyprotic acid? And I would add that to the list of things that you could describe an acid or a base as, right? So I can ask you a question. I can put H2SO4 up on the screen and I can say, label this with all of its possible definitions. One of the definitions you would get is a Bronsted-Lowry acid. One of the other definitions you get is a polyprotic acid, and so on and so forth. Right? The last definition we have. So there's 3 different definitions of acids and bases. The first was the Arrhenius definition, and that was in section 1. The second was the Bronsted-Lowry definition. It's the most common, and that was the one we just went over. And this very last one is the Lewis definition of an acid and a base. So get all of them organized and in your notes, and let's go through Lewis acids real quick. So Lewis acids are going to be molecules that are able to accept electron pairs. Okay, so think of these definitions of acids and bases as going from very, very, very finite to very broad. So the Arrhenius definition of an acid is a very finite set of things. Only a very small number of molecules fit into that little definition. Now, in the Bronsted-Lowry definition, we open it up a little bit more, and more things fit under that definition, but it's still very restrictive. Now, the Lewis acid-base definition kind of encompasses a lot more. It says that when we get an atom or a molecule that has an electron pair, if it can accept an electron pair, it's considered a Lewis acid, and vice versa. If it's a Lewis base, it should be able to donate an electron pair. Okay. Now, this is all going to be based on Lewis structures, Lewis acids and bases, Lewis structures. So again, I'm going to refer you to go back and look at your notes over Lewis structures, because that's how you're going to determine if an electron pair is there or if an electron pair needs to be accepted. That being said, this is going to be, again, the broadest definition. A bare proton, so a proton that has nothing attached to it, is able to accept an electron pair because it's positively charged. So a dead giveaway for a Lewis acid is going to be something that's positively charged. And a dead giveaway for a base is going to be something that's negatively charged. Right? So all you have to be able to do is take on electrons. If you're positive already, you can take on electrons. In fact, you want to take on electrons. For a Lewis base, we're going to see the opposite. We're going to see that we actually want to we want to donate an electron pair. So if we're negatively charged, we're going to be able to do that. Now, in the particular case of any Lewis acid or base, they do not have to have hydrogen in order to be considered an acid or a base. The whole point of this definition is we get away from a finite definition. And what we're doing is we're adding a huge subset of compounds to our definitions of acid and base. So any compound where the central atom has 3 electrons, so think anything in that, the group right after our transition metals, right? Group 13, where we are able to form only 3 covalent bonds, like all of the atoms in the column with boron. Those are all going to be things that can act as a Lewis acid. Okay? So there are all of our different definitions kind of in one small table. Very, very useful to have these handy when you're doing your quiz on Friday. Remember that Arrhenius is just kind of a general, hey, if it produces protons, or H3O+, which is also just a water carrying with a proton, then it's an acid. If it produces OH- ions, then it's going to be a base, right? Bronsted-Lowry takes it a step further and just kind of says proton donor, proton acceptor, and Lewis makes it the broadest definition it can be with electron pair acceptor, electron pair donor. You really do need to have a good grasp on Lewis structures in order to spot those Lewis acids and bases. And that is the end of lecture for today. Please ignore this one in the middle. I forgot to add some Lewis acids and bases. We will go over this in our in our Zoom meeting later today. But please do the first one, the third one, and then, this one, and this one. So the last 3. Okay, so skip the second one, but do these other 3, I guess. Define the Bronsted-Lowry acid base, define the Lewis acid and base. This will be helpful for your quiz. And then name compounds that are acids under Lewis, but not acids under Bronsted-Lowry. Right, so you're looking for compounds that don't have protons, but are electron acceptors, right? So you're looking for acids in that particular question that are electron pair acceptors, but are not going to have protons attached. Okay? And your book should be helpful with that. That's all. See you later.